All right, everybody, welcome back. Today, we are going to look quickly at a sketch of the proof of Wiles' main theorem. I'll remind you what that says right now. It says that if I have a Galois representation, rho naught from GQ to GL2K, where K is a finite field, characteristic P, where P is a prime at least 3, satisfying conditions A through D that we discussed over the last couple of videos, then there is a natural map from the universal type D deformation ring to the universal modular type D deformation ring, which I'll call phi sub D. And D here is just any deformation type of rho naught. The claim is that this map is an isomorphism of complete intersection rings. And as I mentioned last video, a driving engine behind the proof of this is what's called Wiles' numerical criterion. And here's what it says. It says, let R and T be coefficient rings and let O be a complete discrete valuation ring. Suppose there is a commutative diagram of surjective arrows, R to T to O and R to O. Let IR be the kernel of this pi R map here. Let IT be the kernel of this pi T map here. Let A to T be the image under pi of T of the annihilator of I of T, which lives in T itself. Then the following are equivalent. Phi is an isomorphism of complete intersection rings. IR mod IR squared is finite and its size is less than or equal to the size of O mod eta sub T, or I mod IR mod IR squared is finite and its size equals the size of O mod eta sub T. And we'll be covering this criterion in chapter 11, as I mentioned last time. And then just very quickly review a corollary to this is that if rho naught satisfies conditions A through D, then every type D deformation of rho naught is modular. And over the next couple of videos, we'll be looking at how to use that fact to finish off the proof of Fermat's last theorem. Let's look at a sketch of the proof of Wiles' main theorem first. Let's suppose F is a weight 2 nu form, such that rho sub F from GQ to GL2 of O of F is a type D deformation of rho naught. Here, O of F is the ring of integers in the number field attached to F, which we'll call K sub F. We know such an F exists by the ABCD theorem, which we covered a couple of videos ago. We also know by the universal property of the universal type D modular deformation ring that there's a unique homomorphism, a ring homomorphism, which we'll call pi sub T sub D, from T sub D to OF, commuting the lifting triangle. So what we have is something like this. Okay, we have GQ to GL2K, that's rho naught. Okay, we're lifting to some modular deformation, rho sub F to GL2 of OF, and we've got the universal modular deformation up top, GL2, CD, and that's called rho sub DM. And the point is, what I'm saying is this diagram commutes here, and here's my ring map, pi sub T sub D. Okay, now, well, here's what I'm going to do. I also remember have this map from R sub D to T sub D given by phi sub D. So there's actually another triangle living above this to GL2 R sub D, and a map that goes like this, right? And we called that's our phi sub, or yeah, that's our phi sub D. Okay, what I'm going to do is I'm going to define pi sub R sub D to be pi sub T sub D composed that map phi sub D. And this is the map I'm trying to show is an isomorphism of complete intersection rings. In other words, all that said, I get a commutative triangle like this. I have my map R sub D to T sub D given by phi sub D. I want that to be my isomorphism of complete intersection rings. Here's the pi sub T sub D that exists by universal property. Here's a pi sub R sub D that exists by just defining it to commute this triangle. Okay? What you do is you show all three arrows here are surjective. That these two are surjective follows immediately from the fact that these maps are O sub F algebra homomorphisms. And then you can pretty easily see that phi sub D is surjective. The claim is to show that phi sub D is an isomorphism of complete intersection rings. Now, O sub F here, this is definitely a complete discrete valuation ring because it's the ring of integers of a p-adic completion of a number field, the number field attached to F. And so all conditions are satisfied for me to go up here and to use Wiles' numerical criterion. And the key is we want to show that number 2 holds. If we can show that, we're done. So we got the surjective arrows, we've got the complete DVR down here. I just need to show that IR mod IR squared is finite and that its size is less than or equal to the size of O mod eta sub T. Okay, so how is that done? The way that's done is okay, so you've got this inequality here. Now, I'm just going to be loose with this. I'm going to call this kernel here still I sub r. Okay, and I'm still going to call eta sub t whatever it was before. I'm not going to change my notation to account for the fact the names of these maps changed between here and Wile's numerical criterion. Okay, so we've got this inequality, right, that we want to show. We want to show I r mod I r squared is finite and has size less than or equal to the size of OF mod eta sub t. So how do you do that? What you do is you interpret both sides in terms of well-studied objects from the very rich field of algebraic geometry. Instead of working with IR mod IR squared, you can work with its vector space dual homo f from IR mod IR squared to KF mod OF. So you just, instead of thinking of this as like a vector space, you're thinking of it as you're going to work with its dual instead in some sense. Okay, well, imagine this as a tangent space. This space, it turns out, so this dual space can be identified with what's called a Selmer group, which is a certain special subgroup of a Galois cohomology group. I have a whole chapter on Galois cohomology coming up, chapter 4. It's what's called H1 sub D, so corresponding to the deformation type D of GQ, comma, add 0 rho f tensor KF mod OF. And that's just a subgroup of a Galois cohomology group that's labeled in the exact same way, except for there's no D down here. Okay, and basically what's going on here is you take this Galois cohomology group, whatever this means, and you look at a certain special subgroup of it, which is determined by the local properties associated to D. Remember, D is a deformation type, so D is equipped with a list of conditions we want to impose on deformations of rho naught, the so-called type D deformations. Okay, this subgroup of H1 here, this is also going to depend on those conditions attached to D, basically, is what's going on here. Okay, then I'll interpret this side over here as what's called a congruence module, and this will be something that classifies congruences between the F that I'm working with here and certain other new forms. And actually, we'll call those certain other new forms type D new forms, going along with the notation and terminology we've established thus far. Okay, so you reinterpret both sides in terms of algebra geometric objects. We'll cover all this in chapters 4, 12, and 14. We'll give definitions, we'll give properties, we'll give all that stuff. And then, so how do you actually prove the inequality? So you've reinterpreted these sides. How do you prove this? You have to prove it in two cases. First, you prove it in what's called the minimal case, which is where sigma sub D, the set of primes, the finite set of primes associated to the type D deformation itself. This is the case where that set of primes is empty. This has to be dealt with separately. And we will actually do this last. We'll do the non-minimal case first. Then what you do is you deal with the non-minimal case via induction on the number of primes in sigma sub D. So what you do is you have to somehow keep track of how the Selmer groups on the left-hand side of that inequality are growing. And you have to keep track of how the congruence modules on the right side are growing. Both of these things delicately, how are they growing at the same time as sigma D grows? You need to figure that out. And so what you do is inductively, you're trying to conclude that the inequality, if the inequality from the numerical criterion is satisfied for one type D deformation, it must also hold when additional primes are added to D or sigma sub D, if you like. Okay. So again, minimal case, sigma sub D is empty. Then we go by induction. And we show essentially in the non-minimal case that if the numerical criterion is satisfied for one type D deformation, then it must hold when additional primes are added to sigma sub D. Okay, the primes attached to the deformation type D. Okay, and so we will be presenting in chapters 12, the non-minimal case, and 14, the minimal case, simplifications of Wiles and Taylor's proofs. And I will see you all in the next videos for that. Although in the next video, we'll just be wrapping up the proof of semi-stable modularity. We won't be getting into any of these details for a while.